In today's video, we're going to talk about this oscillation and simple harmonic motion. Let's just start with the basic. Simple harmonic motion, or SHM. So SHM is a short term of simple harmonic motion, is a kind of motion that's repetitive, back and forth, and follows a predictable pattern. And you've probably seen it in a spring bouncing up and down. But what makes this motion simple and harmonic? Well, it's all about the restoring force, a force that always acts to bring the object back to its equilibrium position. And the key equation here is the Hooke's law, which will be shown as F equals to negative kx. And which F is the restoring force, K is the spring constant, and x is the displacement from the equilibrium point. And I want you guys to think, why do we have the negative in Hooke's law? So, well, it's just a simple idea, but that just means that the force always acts in the opposite direction of the motion. So let's try to visualize a simple harmonic motion using the spring. So if, for example, I have a table here, and like there's no friction here, a frictionless surface. And then I have my spring over here. For example, this is our oscillator. And then we're going to measure this point. That's the point that we're going to measure. These are the maximum point that the oscillator can reach from the equilibrium position. And this is, for example, our equilibrium position. Now, let's say, if you try to look at this, the motion of it, that one goes back and forth, reach the point, reach this position and goes to that position, and again goes back and forth. So if you try to look at the point from down there, what you will see would be something similar to this. Now let's call this that axis, for example, it's x-axis. This one is the maximum displacement, and this one is the maximum displacement from the equilibrium position. But this one, since it's to the right, we call it positive amplitude, maximum displacement from the equilibrium position. And since this one is to the left, we call this minimum displacement from the equilibrium position. But again, they're like maximum displacement, but this one is to the negative side. So now, for example, this one this one is the oscillation range. Oscillation range. And then what you will notice is our dot, which is here, for example, try to goes to this point and then goes back to the negative a, goes up to positive a, goes back to the negative a. And that's what we'll be seeing. These points are called the turning point. And if you want to imagine it, for example, this point, when it reaches there, when it's reached here, it goes back. And then when it reaches there, for example, it goes again up. So that's what we will see. The motion, if you look at it, is a sinusoidal, indicating that it's a simple harmonic motion. And the motion is symmetrical about the equilibrium position. And the maximum distance to the left and to the right is a, which we call as amplitude. And the x, our x in the Hooke's law, is measured from the equilibrium position. So, and here is the equilibrium position that we will see. So we imagine it and we try to visualize it. So that oscillator oscillates. The back and forth motion continues around the equilibrium position. And now let's define some important terms. Amplitude, or A. As we said, amplitude is the maximum displacement from the equilibrium. What is period? Period is exactly time for one full oscillation. Time it takes for one full oscillation. Time for one oscillation. So if you can guess, here for example, we have a point right here. It goes right there, goes down, and then it reaches here. So this is our full oscillation. So this is not the exact position, but here, for example, this is our full circle. So our T would be here. I would try to show it in another graph. And then I just try to like give you a better understanding of what period is. Frequency is the inverse of the period, and it means the number of cycles per second, and it measures in hertz, and this one is measuring time units, which is for example, mostly seconds. And notice that the relation between them is T equals to inverse of F. And then we're going to talk about this more. Angular frequency, or omega, is the related to frequency by omega is equal to 2 pi f, or it can relate to the period by 2 pi over t. And then we get to the equation of, let me first draw the like this graph here, but then in better terms. So we have a term, we have a graph here. This one called position from the equilibrium position, x, and this one is our t. This one, for example, we measure it at meters, and this one in seconds. So we have the positive amplitude, and we have the negative amplitude. So it goes, for example, it follows this motion. It follows this motion. So what is t here? So from the maximum point of this one to the other one, it's called t, or the time that it takes for one full cycle. The amplitude, we have it here, and omega is 2 pi over t, or 2 pi times f. Here's the equation to describe the simple harmonic motion. It says the x, the displacement from the equilibrium position, is equal to a cosine of omega t plus phi, which is our phase. So a is our amplitude. Omega is angular frequency. T is time, and phi is the phase constant. So now try to learn this equation. For example, we said x is the displacement from the equilibrium position, which are the points here. This is our equilibrium position, this is our equilibrium position. Then do we have like the minimum, when are we at the equilibrium position? When the amplitude is 0, right? So to get the amplitude of 0, the cosine of omega t plus phase difference, in this case the phase difference is 0, so we do not consider it. So cosine of omega t should pi over 2, or the 3 pi over 2, 5 pi over 2, or and so on. And so, for example, the pi over 2 is 90 degrees, so cosine of the 90 is 0, and then when we get 0 here, 0 times amplitude is 0, and our x would be 0, so which means that we're at equilibrium position. So when do we have our maximum displacement? It's when we have the cosine of 1. Cosine of omega t equals to 1. And when is that? It's, for example, at 0, pi, and so on, 2 pi, and so on. It goes on. So that's how can we drive, and that's how we can visualize better the formula by trying to like going deep down on it. And now let's go a bit deeper. We can relate Newton's second law to the Hooke's law. And how can we do that? So what does the Hooke's law say? It said that F, restoring force, equals to negative kx. And what does this Newton's second law say? It says that F equals to m times acceleration. So we can say that negative kx equals to ma. And then using that, a can be said that equals to negative k m times x. So, and again, using this formula, that formula, x equals to a cosine of omega t plus v. If we take the derivative of it, we get this one, the formula for the velocity, and which is negative a omega sine omega t plus v. And then if we again take the derivative of the velocity graph, we get the acceleration, which is negative a omega 2 cosine of omega t. So what is, and if we try to again take the integration of the acceleration graph, we get the velocity, and try to take integrate from the velocity, we get the integration derivative. So what is derivative? Derivative is basically the slope of a graph, and what is integration is basically the area under the graph. So for example, we have, let's draw another graph over here. I want to visualize it. Okay, it's a good idea to draw it like this. So now, for example, let's say that's our motion, right? We said that the derivative of our motion is equal to the velocity. So the slope of the graph at any moment, for example, at moment 0, it's here, right? So the velocity here, what is the slope here? It's 0, so the velocity is 0. And again here, the slope is 0, so the velocity is 0, slope is 0, so the velocity is 0. When do we have our high slope? It's when we are passing the equilibrium position. So here's the maximum velocity. And again, here is also the maximum velocity. And if we try to draw our velocity graph, and then we take the derivative of that, we get to the acceleration graph. So notice that our graph is it's going down like this. It's straight line, and then it goes down. As we get to this point, it again goes up, and then it goes down. It's just like there's a phase difference between them. So I would draw them. So this is our position graph, and then if you try to get the derivative of it and use the graph that we just drew, we try to draw the velocity graph, it would be, notice that here is 0, right? So we start at a point 0, not the amplitude. And then these are not called amplitude anymore, they call omega a, as we wrote, and omega is 2 pi f. So the point is 2 pi f a now, and this is negative 2 pi f a. So the point here is 0. So we start by point 0, and we go down as I've just shown you. It goes down and it goes up again. So it would be, let me draw this. So we again hit the point 0 here, and we have the maximum velocity over there. And then here also we're going to hit the 0 again. So our graph would be something similar to this one goes to the maximum. Look, this one goes to the maximum, so it goes down here. Then it reaches 0, so it goes up. Then it goes to the maximum, positive, but here this time it's at positive because the slope is positive. Here the slope is negative. Look, negative slope, positive slope. So here is our maximum, and then but it's going to the 0 again, so it goes up, down again, and so we can see that how it works. So if we try to take a derivative from this graph, and again, look, the derivative is just this slope, but notice, unlike the graph that we have for the velocity here, which is started by the straight line, the slope of a straight line, the slope of 0, the velocity is 0. But now we don't have a slope of 0, so it's the maximum slope that we have. So it is start by this point, and it's negative. The slope is negative. the slope is negative, so it would be something like this. Slope here is 0, right? So if you start by this point, it goes up, and then it goes like this, goes down, and that's it for this point. But yeah, we can just draw it like go up and down. And that's for our acceleration, and notice that now we have to use omega 2a, so this is not called amplitude anymore, it's 2 pi f2a, and here is negative 2 pi f2a. So that's how we will try to draw our graphs. So let's get back to the concept here. We get to the drawing of each graph using the formula and the derivative of that. So now if you try to, like, for example, if we try to get the integration of this area or like this area, we get to our velocity graph, and then if we try to get the integration of this area, for example, we get to our position graph. So now let's, as we said, let's talk about that simple harmonic motion transferring energy. So simple harmonic motion is all about transfer of energy between kinetic energy and the potential energy. So if you remember the kinetic energy formula is K equals to the half mv square, and the potential energy in the spring is U equals to the half kx squared. And the total mechanical energy equals to the U plus K. At maximum displacement, at point like this, 0, this is our equilibrium position, this is positive amplitude, this is negative amplitude. At maximum position, right, at our amplitude, since we are going to the turn like this, for example, it starts like this, it turns over there, so this is this slope, as we just said. At amplitudes, for position graph, we have the velocity of 0. When the velocity is 0 over here, right, so the a half of mv squared is again 0, so our k is 0. E minus k equals to u, so our u is our potential energy is at 100%, it's maximum. But notice here, we have the maximum velocity over here, so our mv squared, half mv squared, would be the maximum value. And there is no displacement from the equilibrium position, so the potential would be 0, because our kx now is 0. So half k times 0 would be again 0, and E minus k equals E minus u equals to k, so our k is maximum. So the point is, at the amplitude, we have the maximum, let me just draw 100%, we have 100% of potential energy, and at equilibrium position, we have 100% of kinetic energy. And that's it. The total energy remains constant. So I guess there is a graph for it, like on how we try to show the energy, total mechanical energy, and like the kinetic energy with it. It's like this. So we have our graph here. This one is positive amplitude, negative amplitude. We said the mechanical energy remains constant, so it would be, for example, a straight line like this, and we call it E. Then we have our kinetic energy, which is 0 at the amplitude but maximum. This is our equilibrium position. This is but at equilibrium position is maximum. So it would be, let me draw it with red. Okay. We have 0, it goes to the maximum, and it goes to the 0 again. So this is our kinetic graph, kinetic energy graph. Then we have our potential energy, which is maximum at the amplitude and 0 at the equilibrium position. And notice how they are like exactly inverse of each other. And to give you a better understanding on what we are going through, so let's walk through an example. Imagine a 0.5 kilogram cart is attached to a spring with K equals to, for example, 200 newtons per meter, and the amplitude is 3. So what is the total energy? The total energy here, we can, like, you might say, how can we calculate it? We don't know at what position. The total energy at amplitudes are equals to the potential. So the total energy at amplitude, as we said, it's equal to the potential because we have 100% of potential energy. So we can just 3 centimeters, for example. So we can just calculate it. E equals to U, potential energy, and that potential energy equals to half Ka2. And we drive this equation using that Kx2, and so we have the maximum mx here is the maximum displacement, which will be shown as a. We just say instead of half Kx2, we just show it as half Ka2, and they're similar, but so since we want to like calculate that amplitude, we just show it with a so that we show that it's an amplitude. So it would be half times 20 newtons per meter times, notice that this is centimeters, so we just have to convert it to 10 with the power of -3. So it would be 10 on power 2 here. This is -6. So we will get 0.009 joules. 0.009 joules. And now let's say, what is the max speed? So we said the total energy is 0.09 joules. The max speed is half mv squared, and then equals to the 0.009 joules. And then if we say, okay, if we try to move it along, we can say this one times 2, this one times 2. We say mv squared equals to the 0.018, and then we can divide it by m, divided by m, the square root to so that we just calculate the velocity equals to the square of 0.018 over what was the math? Okay, half. So our answer would be square root of 0.018 or 0.5. We get something like 0.27 meters per second. And now if we go for the velocity, for example, there is another equation for the velocity. I forgot to mention that. The Vmax is a omega, and omega was a square root of k over m. So we can just say a times square root of k was 20 over 0.5, and that's it. And we can just calculate this, and again, I guess we get the value of 0.27 meters per second. And now it says, what is the velocity at x equals to 2 centimeters? What is the velocity over there? So there's again another formula, which is v equals to the square root of k over m times a square minus x2 square. And then if we try to put the values in, we get the value of we get the value of 0.18, but notice that there is a positive negative here, so positive negative 18, 0.18 meters per second. Now let's try to solve these two problems. Please pause the video and then try to solve it. It says the position of an air track car that is oscillating on a spring is given by x equals to 12.4 centimeters cosine of 6.35 radians per second t. At what value of t after t0 the air car first located at x equals to 847. So let's write the formula. It says x equals to 12.4 times cosine of 6.35 times t. What does this tell you? What was the formula for simple harmonic motion? A cosine of omega t plus v, which since we don't have any v, this one is 0, so it's just a cosine of omega t. So 12.4 is our amplitude. Sorry guys, it's our amplitude. And 6.37, it's our omega. So it wants at what time of t the x equal to 8.47, and if you just have to put it in the formula, 8.47 equals to 6.35 t, and that's it. We just have to calculate this now. So we say the cosine of 6.35 t equals to 8.47 over 12.4, and the answer would be 0.683. So now how can we calculate it? We just have to say that 6.35 t equals to the inverse cosine of 0.683, and then this number divided by 6.35 gives us the value for the t, and which will be t equals 0.129 seconds, and that's the answer for it. If you have any more problems, please comment it. And now let's get to our second one. It says an object moves with a simple harmonic motion. If the amplitude and the period are both double, the object's maximum speed would be what? So we said the maximum speed is omega a. So an omega would be 2 pi over t. So the formula for the maximum speed would be a times 2 pi over t. The question says the amplitude and period are both double. So we have 2a times omega over 2. Again, it's the same thing. So the object's maximum speed remains the same. And that's it. I hope you guys have learned something, and if you have any more questions, please comment it. Thank you for watching my video. Please like and subscribe.